Okay, hello. Let's start the fourth video now. So we're still in the subcortex. We're about halfway through now. So, Moxham wants to know a particular set of nuclei juggling between the thalamus and the hypothalamus. So you need to know all of the hypothalamic nuclei and a baseline of their functions, which we previously covered. You don't need to know all of the thalamic nuclei. There are an awful lot of them. If you want to, you can, but it's very histological, it's not gross anatomy, and the boundaries of their functions shift quite a bit. So, ventroposterolateral and ventroposteromedial are of the thalamus, and the VPL conveys ascending sensory information from the spinal cord. So it's the non-head sensory information that synapses there, so the third order neurons, cell soma arises within the VPL. Right, whereas the trigeminothalamic tract, the head is the VPM. Okay, so the ventroposterolateral is from the ascending tracts of the spinal cord up to the primary somatosensory cortex and the association regions, and the VPM is the trigeminothalamic tract. Now your geniculate nucleates, your geniculate nuclei, medial and lateral, are both constituent of the metathalamus, not epithalamus, don't get them confused. They are the metathalamus. They are not technically, in anatomical terms, classed as constituents of the thalamus. You'll often see them classed as such incorrectly in books, but they are the metathalamus. The medial geniculate nucleus is auditory, and the lateral is visual. So make of that what you will. In the visual pathway from retina to occipital lobe, we do go through the lateral geniculate nucleus, which you should know. The medial geniculate nucleus is where the bilateral auditory tracts ascend to before going onwards to A1, which is, if we remember, the transverse temporal gyri or Heschel's gyrus in the lateral sylvian fissure deep in there. We move to a collection of hypothalamic nuclei. So we have our suprachiasmatic nucleus, and we have our supraoptic nucleus. Now our supraoptic is oxytocin in the posterior pituitary gland, but our suprachiasmatic is circadian. So what a nice, simple way to remember them. The C's and the O's. Okay, your paraventricular nucleus is oxytocin in the posterior pituitary gland, also ADH, so these are ADH secretors as well. Some texts will say that one does more than the other, but oxytocin and ADH, right? That's all we care about, really. The mammillary bodies are at the end of the anterior fornix, which is that big, long projection of fibres that we have seen many times already. Coming out of the hippocampus. So you've got hippocampus and dentate and subiculum going up, blah blah blah. We have the fimbride and the fornix, and anteriorly we come to the mammillary bodies. And thiamine deficiencies cause Wernicke-Korsakoff syndrome. So the bilateral ablation of the mammillary bodies cause Wernicke-Korsakoff syndrome, which is block 3. So just a little quick overview here. We're just briefly mentioning the fornix here. So this is what the tracts of the fornix look like. So we have the pillars of the fornix, the body of the fornix, and then the fornix bifurcates here to fimbriae, and then we have our hippocampus here. And the hippocampus, sat on it here is the uncus, and within the uncus, deep to it, obviously we know we have the amygdala, which is using the stria instead to project forward. So not the using the stria terminalis to project. If that doesn't make sense, you don't worry. We have other videos on that, so don't worry about that too much for now. And then just make sure that you can see that the fornix is here. Here's our fornix. Here's our caudate head. Here's our internal capsule, septum pellucidum, ventricles, corpus callosum. So you follow the fornix round, we have fimbriae, we have hippocampus here. So, vascular supply of the pituitary gland. So, let's orient ourselves first of all. Anterior is here, posterior is here, so we have our optic chiasm, mammillary bodies and the hypothalamus. Our supraoptic and paraventricular nuclei come down here and supply oxytocin and ADH to the posterior pituitary gland. So we have a superior hypophyseal artery. Remember, hypophyseal is the old term for the pituitary gland. and it supplies this capillary plexus here, which nourishes the infundibulum and the pituitary gland, and also we have secretions of our hormones into here so that the hypophyseal veins can convey this to the body. So superior hypophyseal will supply most of the anterior, inferior has its own bespoke section for the posterior pituitary gland. So just note there that the inferior hypophyseal artery is separate to the superior hypophyseal artery circulation. There is a divide between them there. So your superior hypophyseal artery, it will be safe to say, supplies the infundibulum and the anterior pituitary, and your inferior, it will be safe to say, supplies the posterior pituitary. There's obviously going to be anastomoses and variable overlaps here in the capillary beds because they are incredibly variable, but that is that. So the epithalamus, we've already said, consists of three things. The habenular, which is this portion here, here and here. The pineal gland, which is here, and the stria medullaris, which is a sort of projection. So the habenular is anterior to the superior colliculus. The physiology is that it's connected to the basal ganglia. So it's a connection by which the pineal gland and basal ganglia can talk to each other. So the stria medullaris is a white matter tract that connects the habenula to the basal ganglia as well. So it's a secondary connection. And the pineal gland is green here. It sits above the superior and inferior colliculi, which collectively are called the corpora quadrigemina, or four-bodied twins. And then the physiology is that it secretes melatonin when darkness is seen in the retinohypothalamic system. So the retina detects a change in the ambient lighting. It's dark, so the change in the firing rate of the ganglion cells informs the suprachiasmatic nucleus of the time of day, and thus the melatonin is secreted or not secreted. Melatonin is secreted in the dark. You take melatonin if you want to sleep. Okay, melatonin is not secreted in the light. Well, it is, but not a lot. So, anatomy and functionality of the anterior and posterior commissures. So remember we said that commissures are white metal tracts collecting the two hemispheres. Our big bad boy of commissures is the corpus callosum, right? But we have two other commissures. We have an anterior one and we have a posterior one, okay? So this little swelling here should also be in green, Ken Hub. So we have our anterior and we have our posterior commissures here and here. Okay, and here's basically what they look like. So here's the anterior commissure connecting there and then going up and down. So it connects to a whole set of things. So it connects to the temporal lobes, and its physiology is involved in olfaction, pain, etc. So if you have the old-fashioned epileptic treatment, which was the callosotomy, which divided the hemispheres so you couldn't go from a foci to a global seizure, this callosotomy here, you were still able to have a communication subcallosally through the anterior and posterior commissures here and here. So there was still some communication and preservation of particular functions, in particular olfaction and pain bilaterally. So the pain network. Posteriorly, it links the epithalamus. So remind yourself as to what the epithalamus is. And the physiology of the posterior commissure is that it's involved in the pupillary light reflex bilaterally, which is neuroophthalmology here. So just to remind you very quickly, have a quick look at a video of this on YouTube if you don't remember this so much. But cranial nerve 2 is your afferent supply, and your efferent supply is cranial nerve 3. Okay, so cranial nerve 2 comes from the eye. Oh, there's light that's sensed here. Let's say that we have the torch here. So, there's light. So, cranial nerve 2, message propagates via cranial nerve 2 to the midbrain, and it goes to a number of things. It goes to the pretectal nucleus here. It goes to the superior colliculus, and then it uses the posterior commissure here to get to the contralateral one as well, because we want the pupillary light reflex to be light is shone in one eye and both pupils respond quickly to protect the retina from damage from the light, right? Because it's so sensitive. So our Edinger-Westphal nucleus, which is also now called the accessory oculomotor nucleus, projects the efferent limb via cranial nerve 3 to the sphincter muscle, sphincter pupallae, to contract. Now it's a 2-neuron arc. This is a bit of a mess now, isn't it? It's a 2-neuron arc, so we go from the Edinger vesical nucleus to the ciliary ganglion, and then the short ciliary nerve conveys it to the sphincter pupallae muscle. The actual detail of this is probably not so important unless you're going into ophthalmology itself, but the pupillary light reflex is useful because it tells you the function of the posterior commissure, connecting both eyes for the pupillary light reflex to be consensual. So here's a reminder of a few different things. So we've got our lamina terminalis here, which sits anterior to the hypothalamus. We've got the fornix here, and just remind yourself as to what the fornix terminates as here. So the fornix are running along here, and then we have our hippocampus is here, our fimbri are here, and this serrated area here is our dentate nucleus. Okay, so we've got brainstem here, so hypothalamus, hypothalamic sulcus, thalamus here, pineal gland, so our posterior commissure is here, anterior there, posterior there. So, pause here, and can you find these different structures? We're not going to go through them now, they've all been covered in previous lectures. We're spiral curriculum and building this detail up. Can you tell me what it is, what is near to it, where it is, what it does, so the basic anatomy, the basic physiology, and are you starting to think about its blood supply? Is it anterior cerebral, is it middle cerebral, is it posterior cerebral? Are there particular branches that supply it? Obviously we will have a vasculature lecture, but you need to be able to tell me the anatomy, the physiology, the vasculature, and close relations of all of these names that are coming up over and over again. So our pineal gland. Here it is, which is part of the epithalamus. You need to remember the habenular connection, you need to remember the stria medullaris coming on, you need to remember the corpora quadrigemina here, and it all sits above the cerebellum there. So, epithalamus, as we've said, produces melatonin, which modulates the sleep pattern. Melatonin is secreted in the dark. Okay? So, moving on, the thalamic nuclei, again, not going to mention them. This is a handful of them, there's many more. And new ones are being discovered, and there's turf war as to what constitutes what, and there's functional and anatomical classifications and histological classifications, and it's just an absolute mess. There are a whole number of them. You have a set number of them that you need to know, which we have already mentioned at the very beginning. You need to know VPL, VPM, and the metathalamic nuclei there, and then you need to know for absolute those for hypothalamic. So that's core. You need to make sure that that is what you know, but that's all we will do for thalamic nuclei. The subthalamus we've already mostly covered, but we've covered the motoric component of it, which is that it projects to the globus pallidus internus for the most part in the indirect pathway of the basal ganglia. So go back to that lecture where we talked about the basal ganglia's pathways and go back to your block 3 notes about that. There are two other functions of the subthalamic nucleus which we won't touch on much. There's oculomotor, but there's a cognitive and behavioural component as well that projects to the pallidum and projects to the substantia nigra. So beware that that is another sort of association, but again, it's only an association. It's not a definitive source of its supply. It's a modulatory thing. And look how much of the subthalamic nucleus is motor components projecting to the globus pallidus internus. It's 90% of the thing, right? So here's the indirect pathway, a little summary of them. And remember, if the subthalamic nucleus is knocked out, the consequence is that the subthalamic nucleus cannot be the handbrake for the thalamus. The whole point of the basal ganglia is to modulate and fine-tune movement. The dumb primary motor cortex wants to fire but sends a collateral to the putamen saying, can I fire? The basal ganglia processes that permission slip, yes or no, and the subthalamic nucleus is that end product where if absolutely no, this is an inappropriate movement, this shouldn't be happening, this is an aberrant firing input that's annoying and we need to stop it, subthalamic nucleus projects an inhibitory fibre up. Ultimately, that means that the thalamus is inhibited. So thalamocortical projections do not go. The result is this hemiballismus that we talked about, okay? Bang. So go back to those if you're not comfortable with those. Now, the zona insertion in the fields of Forel are something that we're going to briefly talk about here. So you've seen this many times, caudate, lentiform nucleus here. Here's our subthalamic nucleus, which is what we talked about. The fields of Forel is just a collection of fibres that connect the thalamus to the lenticular nucleus, some of them running down here quite inferiorly. So you just need to be aware that these things exist, and you might see them referred to as certain different things, prerubral, lenticular, fasciculus, but they're just a collection of projecting fibres that are involved in the basal ganglia loops. And the zona incerta itself here is within the internal capsule, between the thalamus and between the between the lentiform body here. And the zona incerta itself provides GABAergic subthalamic projections to the thalamus. Okay, so it's this, it's the output of the subthalamus to the thalamus to regulate it, as we've talked about. Whole other functions, appetite, sexuality, but the inhibitory and direct pathways handbrake is pretty conclusively seen. It's what we like. So I've put the shrugging emoji because we're not entirely sure, but you might see a little grey blob in the internal capsule, and I just want you to know that is the zona incerta. Okay, so fields of Forel, again, we've talked about it. It's this whole region. It doesn't include the zona incerta, but there are 3 different sections, and they're just white matter tracts linking the subthalamic nucleus to the thalamus and the basal ganglia. So it's a bit like the zona incerta. It's all of those connections, and it's how the zona incerta and the fields of Forel are how the basal ganglia talks to the diencephalon, basically. Habenular nuclei, good news, thumbs up, we have done that, we have covered it. The specific nuclei within the habenula is not particularly useful. Just remember that it is epithalamus along with Stria medullaris and along with the pineal gland, and it's connecting the pineal gland to the basal nuclei. And then that's Stria medullaris, as we've mentioned a few times. So if we have a projection anteriorly here, we've sort of said here, here's the pineal body, here's the habenula, and then the Stria medullaris sits on top of the thalamus here and connects it to the anterior nucleus of the thalamus. So it runs from here all the way to here. Okay, so it basically runs to the foramen of Monro, that connection between the two thalami, between the two the two ventricles there. So it sort of arcs inferiorly here to the fornix and the corpus callosum. Just something to bear in mind, not really something you can see grossly, but an important component of the epithalamus there. And that's a lecture. Thank you very much.